Today we will talk about sampling distributions and the central limit theorem. We would want to study the distribution of statistics that are defined using a random sample. Before we proceed, let me briefly recall the setup. Let x1, x through up through xn be a random sample of size n. This is to say that the xi's are random variables that have the same distribution for all values of I ranging from 1 through n. The set xi, x1, x2 up through xn is also required to be an independent set of random variables. Conditions 1 and 2 are required for the definition of a random sample. We set script x to be the set of values of the random variables that are inside our random sample. Since all the random variables have the same distribution, the set of values for all of these random variables will be the same set, that is script x. The joint sample space for the random variables x1, x through up through xn is the n Cartesian product of the set script x. This is denoted as script x to the n, and it's an n tuple where the elements of the tuple are elements inside script x. Since x1, x2 up through xn is an independent collection of random variables, the joint probability distribution of x1, x2 up through xn is going to be defined as the function p, which takes in input for an n tuple and outputs the product px of xi. If xi's are discrete random variables, and p sub x is the common probability mass function of all the xi's. If the xi's were continuous random variables, we will be working with the joint probability density function that is constructed using the common probability density function f sub x of x. For brevity in this video, we will generally work with only discrete random variables. The continuous case is very similar. We next talk about statistics. So let t be a statistic for the random sample x1, x2 up through xn. This means that t is a random variable that is calculated using the random variables x1, x2 up through xn. This means that t is a function that is defined on the joint sample space and takes values inside R. The joint sample space in this setting is denoted by script x to the n. We will be interested in the probability distribution function of the statistic t. This distribution is often called the sampling distribution of the statistic t. To calculate the sampling distribution of t, we will use the joint distribution of the random variables x1, x2 up through xn. Now, if p is the joint PMF of x1, x through up through xn, we are assuming that our random variables are discrete. Therefore, we talk about the PMF. Then we want to calculate the PMF of the statistic t. That is, for values of small t inside script t, we want to calculate the probability that the statistic t takes the value t. In this setting, script t denotes the set of all values of the statistic t. Now, for a value t of the random variable, we define e of t to be set of all n tuples on which the random variable t takes the value small t. In this setting, the probability that the random variable takes the value t is just going to be the sum of p of x1 through xn, where the tuples x1 through xn belong inside e of t. And we have noted earlier that the joint distribution function p can be calculated as the product of the common PMF of the x's. We will next talk about the sampling distributions of two important statistics, that is the sample mean and the sample total. Let x1, x2 up through xn be a random sample that is coming from a population that has mean mu and variance sigma squared. This is to say that the expected value of xi equals mu for I ranging from 1 through n, and the variance of xi equals sigma squared for I ranging from 1 through n. In this setting, we can define the sample total for the random sample x1 through xn to be the statistic t naught that equals the sum of the n random variables x1 through xn. The sample mean for the random sample x1 through xn is defined as x bar. This is the statistic that takes the sum of the n random variables and divides out by n. Another way to write this is the sample total divided by n. We next calculate the expected value of the sample total, which is going to be the expected value of x1 plus x2 all the way up to xn. This is going to simplify to as the sum of the expected values of the xi's, and noting that all of these xi's have the same mean, we get that the expected value of the sample total equals n times mu. We can also calculate the variance of the sample total using the properties of variance to get that the variance of the sample total is going to be the variance of the population times the sample size n. Similarly, we can calculate the expected value of the sample mean to equal mu and the variance of the sample mean to equal sigma squared over n. Having defined the sample mean and the sample total, we would be interested in knowing the sampling distribution of these two statistics. The answer to this question is provided by the central limit theorem. We will first work out the central limit theorem when the population is normally distributed. In this setting, we have a random sample x1, x2 up to xn that is coming from a population that has normal distribution with parameters mu and variance sigma squared. Then we will have that for any natural number n, the distributions of the sample mean x bar and the sample total t naught will be x bar is normally distributed with mean mu and variance sigma squared over n, and the sample total is normally distributed with mean n times mu and variance n times sigma squared. This is equivalent to saying that the random variables x bar minus mu divided by sigma over square root of n and t naught minus n times mu divided by square root of n times sigma both have the standard normal distribution. Note that for the central limit theorem to hold for all values of n, especially when n is small, we need the population to be normally distributed. This assumption can be dropped if we have another assumption, that is an assumption that requires n to be a large number. So this leads us to the general case of the central limit theorem. The setting for this case is that we have a random sample containing random variables x1 through xn that are coming from a population that have mean mu and variance sigma squared. We have no more information about the distribution about the population. In this setting, if n is large enough, the distribution of the sample mean and the distribution of the sample total T naught is approximately normal, and it is given by x bar is normally distributed with mean mu and variance sigma squared over n, and T naught is normally distributed with mean n times mu and variance n times sigma squared. This approximation will improve as n gets larger. This is equivalent to saying that the distribution of the random variables x bar minus mu divided by sigma over square root of n and T naught minus n times mu divided by square root of n times sigma approaches the standard normal distribution as n goes to infinity. We will wrap up this video with a brief example. This is the simplest population that contains exactly two elements, that is 0 and 1. The distribution of this population will be the Bernoulli distribution, that is the probability that the random variable takes the value 1 can be thought of as the probability of a success, which we will call P, and the probability that the random variable takes the value 0 will be the probability of a failure, will end up being 1 minus P. Now let x1, x through up through xn be a random sample coming from this population containing 0 and 1. Our goal here is to calculate the sampling distribution of the sample total T naught. So suppose we are working with a random sample of size 2, then our joint sample space is going to contain 4 elements as described here, and our sample total will take values 0, 1, and 2. We also have the formula for the joint probability distribution, and we can use this to calculate our probability that the sample total takes the value 0, for example, and we get that to be exactly 1 minus p squared. The probability that the random variable is going to take the value 1 ends up working with the two elements inside the joint sample space, 1, 0 and 0, 1. And working through this, we notice that this probability is 2 times p times 1 minus p. Similarly, the probability that the sample total equals 2 can be calculated to be p squared. Putting all of this into a table, we get the following distribution table for the sample total when n equals 2. This might be too early to look for patterns, but perhaps you can notice that binomial coefficients are showing up in our joint distribution table. Let's work out the case when n equals 3 and see where this goes. In this setting, our joint sample space is going to consist of the following 8 elements. These are tuples that contain zeros and ones. The joint distribution function is going to be the product of p sub x of x1 times p sub x of x2 times p sub x of x3. It should have been a product up there. The sample total is going to take values 0, 1, 2, and 3. And the calculation of the PMF for the sample total can be calculated as follows, which gives us the probability that the sample total takes the value 0, the sample total takes the value 1, the sample total takes the value 2, which is going to give me 3 times p squared times 1 minus p, and the probability that the sample total takes the value 3 equals p cubed. All of this information can be put into the following probability distribution table for the sample total. You would have already noticed the binomial coefficient showing up, but let's do the case when n equals 4. In this setting, the joint sample space contains 16 elements. These are described in the set here. And the joint distribution function is now going to be the product of the 4 probability functions p sub x of x1 through p sub x of x4. In this setting, the sample total takes values 0, 1, 2, 3, and 4, and the probability distribution table for the sample total can be calculated on similar lines as before as follows. Perhaps now we are ready for the general formula. That is, when n is arbitrary, the sample total takes values going from 0, 1, 2, 3 all the way up to n. And the probability that the sample total takes the value k is exactly given by the following formula, which is the PMF of the binomial distribution with parameters n and p. This says that the sample total has the binomial distribution with parameters n and p, and this makes sense because the sample total is counting the number of ones, that is, the number of successes for a given sample of size n, where each sample entry is an outcome of an independent Bernoulli trial. This setup is exactly the binomial experiment. Now, since the sample total has the binomial distribution with parameters n and p, the expected value of the sample total ends up being n times p, and the variance is n times p times 1 minus p. Also, the central limit theorem says that if n is large enough, the sample total will be normally distributed with mean n times mu x and variance n times sigma x squared, where mu x is the mean of x, which equals p, and sigma x squared is the variance of x, which is p times 1 minus p. To summarize this, we get that the sample total has the binomial distribution with np implies that for large n, the binomial distribution can be approximated by the normal distribution with parameters n times p and n times p times 1 minus p. To summarize today's video, we have introduced the sampling distribution for a statistic. We have spoken about the sampling distribution of the sample mean and the sample total, and we have worked out a few examples. This is all for now. Take care of yourselves, and I will see you around.